probability that a particular point of time the system is functioning. So we define the reliability of a system at time t whose life is described by x, okay. If x is the random variable, so this is defined as RT is equal to probability that x is greater than t. As I mentioned that it is one of the most important characteristics or parameters for the factories, for the manufacturers, for the engineers who are using the systems. Apart from that, so we will analyze these quantities. Let us also look at another term. It is called instantaneous failure rate of system at time t. Okay, so let us define what it is. So this is defined as limit as h tends to 0, 1 by h probability of t less than x less than or equal to t plus h, given that x is greater than t. So given that the system is functioning at time t, what is the probability that it fails just after time t, that is from t to t plus h. So we consider the length of the interval as h, so we divide by h and then take the limit. Then this is called the failure rate at time t. So what does it mean? It means that we are considering failure just after time t, and to calculate the rate we divide by the length of the interval and take the limit as h tends to 0. Is this definition clear?
Yes, sir.
Now let us try to find out an expression for this. Okay, what it is. So this is equal to limit as h tends to 0, 1 by h. Now we can consider this as event A and this as event B. Then we apply the formula for probability of A given B. That is probability of A intersection B divided by probability of B. Now you can easily see that A is a subset of B. So in the numerator I will have only probability of A, and in the denominator I will have probability of B. Is this okay? Is it okay?
Yes, sir.
So now let us put the expressions for this. The numerator is nothing but the probability of x less than or equal to t plus h minus probability of x less than or equal to t divided by probability x greater than t. That is limit as h tends to 0 f of t plus h, that is the CDF of x at t plus h minus the CDF of, see this probability x greater than t is nothing but RT, or you can write it as 1 minus fxt also. Now this limit as h tends to 0 is nothing but the derivative of the density. So if we are assuming the life as the continuous thing, then this is a continuous CDF of a continuous random variable. So it will become nothing but the derivative of that is the density function divided by the reliability function. It is called the failure rate. Okay, so there is a notation used here for this. Usually it is called HT, that is the hazard rate at time t. Okay, the instantaneous failure rate or hazard rate. Okay, so we have derived the formula for a term called the instantaneous failure rate of a system at time t. Okay, that formula we have derived as density function divided by the reliability function, or density function divided by 1 minus the CDF of the function. Is that okay? Can you follow this formula?
Yes.
Now I will consider the reverse part of this also. So we can now write, see this hxt as minus d by dt log of 1 minus fxt. We can write like this also, because if I differentiate log of 1 minus fxt, I will get 1 by 1 minus fxt into small fxt with a minus sign. So minus minus will become plus. So we can also write like this. So this also can be considered as a differential equation, so which we can just solve it. This implies that log of 1 minus fxt is equal to integral of hxt and of course plus some constant. So this is giving a relationship. So this is the reverse relationship. Given the failure rate function, we can determine the CDF and therefore the PDF. And given the density or the CDF, we can determine the failure rate. So for a continuous random variable x describing life of a system, there is a one-to-one correspondence between the distribution, that is PDF or CDF, and its failure rate function. So this failure rate is another very important parameter for the engineers, because whenever they are considering a system, they will be interested in its reliability, they will be interested in its failure rate. At a particular point of time, what is the rate of failure? So let us try to analyze with respect to the distributions that we have studied. So let us look at, for example, exponential distribution. So for exponential distribution, what do we have? We have fxt is equal to lambda e to the power minus lambda t. So what was the CDF? That is 1 minus e to the power minus lambda t. Okay. So what is the reliability? reliability is e to the power minus lambda t. So for a system whose life has an exponential distribution, it has a reliability e to the power minus lambda t. So it is exponentially going down. So it is something like this. That is the way it will look like. If I consider failure rate, okay, failure rate is the density divided by the reliability. So that is lambda e to the power minus lambda t divided by e to the power minus lambda t. So that is lambda, which is very interesting to see that the failure rate for a system with a exponential lifetime is constant. It is not dependent upon the time. So I mentioned to you about the memoryless property of the exponential distribution. So basically the interpretation of that memoryless property is this, that the failure rate is irrespective of the time, it is constant. So the systems which are very robust, they have the constant failure rate irrespective of the time. So in the exponential distribution, failure rate is constant. Is this point clear?
Yes, sir.
Now you can look at the reverse also, that suppose the failure rate constant is given here, okay, lambda, and if you substitute here, what you will get? E to the power minus lambda t, because integral of hxt, that will give me lambda t here, so it will become e to the power minus lambda t. So that is the CDF of the uh, uh, exponential distribution. So you will get the PDF as lambda e to the power minus lambda t. So given the constant failure rate, you will get exponential distribution, and for the exponential distribution, you have a constant failure rate. Let us look at, say, Weibull distribution, which I described as another important distribution for the lifetime. Okay, so consider so what was the Weibull distribution? Weibull distribution is alpha beta t to the power beta minus 1 e to the power minus alpha t to the power beta. Okay, so here you had fxt as 1 minus alpha e to the power minus e to the power minus alpha t to the power beta. So what is the reliability here? It will become simply e to the power minus alpha t to the power beta. Now it is important to analyze this. So here the reliability, of course, as time increases, the reliability becomes less. But if beta is equal to 1, it is exponential distribution. If beta is greater than 1, then it goes faster to 0 compared to exponential distribution. And if beta is less than 1, then it will go slower to 0 compared to exponential distribution. So you can have different analysis here. So for beta is equal to 1, it is exponential. For beta greater than 1, it goes to 0 faster than and for beta less than 1 it goes to 0 slower than exponential rate. So basically, what I am trying to explain here is that you can model various kind of systems using this. You can model those systems which are very robust, even more robust than exponential. You can model those who are less robust than the exponential. So what is the effect on the failure rate? So let us look at the failure rate. Failure rate is fxt divided by rxt. So you will get alpha beta t to the power beta minus 1. Then you have e to the power minus alpha t to the power beta divided by e to the power minus alpha t to the power beta. So this cancels out and you are left with alpha beta t to the power beta minus 1. So as you can see, for beta is equal to 1, it is exponential distribution. So this is constant. So for beta is equal to 1, hxt, that is simply alpha, that is constant. And if I consider beta to be greater than 1, then you will get alpha beta t to the power beta minus 1, that is positive. That means the failure rate increases as time increases. So hxt is increasing in t. So this is called distributions with increasing failure rate. So the life time has increasing failure rate, which is called IFR. Okay. So in reliability theory, these type of notations are used, IFR. So you can think of so many things where it is an increasing failure rate. For example, your mobile phone, as the time increases, the rate of failure increases. Your laptop or any other kind of electronic system that you are having in your home, your television set or many other things. As the time increases, the rate of failure increases. Okay. If I have beta less than 1, then this alpha beta t to the power beta minus 1. So if beta is less than 1, then this will come in the denominator. It means as t increases, this will decrease. So such distributions are called decreasing failure rate distributions. So hxt is decreasing in t. So the lifetime has decreasing failure rate, that is DFR. So these kind of things are there which have very long life. Okay, for example, you have certain elements like uranium and so on, which have very long lifetime. So the failure rate is in fact decreasing. For example, you buy a new automobile and then the shopkeeper, he will tell you that you should use it more often so that the fuel efficiency increases or the engine capacity increases or the strength of the motor increases. Okay. And of course, after you use for some time, then it increases. Like mileage, in the beginning it may be say 12 kilometer per hour, and it will become 16 or 18 depending upon the kind of vehicle that you are having. So such systems are called systems with the decreasing failure rate. So is this concept clear?
What examples
Yes.
comes in equals to 1?
For
Beta equals to 1.
beta is equal to 1 is corresponding to the exponential distribution. So the distributions which are very, very robust, there you will have close to a constant failure rate. Okay, that means the system is there for example, a rock, okay, a mountain or that kind of thing if you consider. So if you consider in the engineering sense, you have very heavy machinery which works for very, very long time. So if you had any occasion of visiting some heavy steel industry or metal industry, so there you will find systems which are there for maybe 100 years or 70 years kind of thing. You will see, and it is functioning as well. Okay. So there are a lot of mechanical systems. Of course, it is not true with the electrical and electronic systems, but a lot of mechanical systems are there which work for very, very long time. Okay. So failure rate is constant there.
Yes, sir. And so beta equals less than 1, we can tell, we can also tell that the human system, that as we
Yeah,
do
so in the beginning you
exercise.
have a newborn child. It has I mean, very low immunity, so the failure rate is high. But maybe once it achieves the age of 5 years, then it becomes robust and things are better. So a person with a age of 15, 20, like what you are, your robustness is much more. And then once the person crosses the age of 50, then it starts going down. Okay, so you can think like that.
Okay, sir. Thank you.
So now when we are discussing the reliabilities of the system, so the system is not a one thing. I mean, it is not a one part of it or something like that. Actually, if you look at any complex system or any manufacturing system or any engineering system, it has many things, many components are there. So for example, when we are having this class going on, what are the components that need to function in order that this class is conducted smoothly? So can you tell what are the things that are required? Can anybody just tell what is required for this online class which I am taking now to be conducted smoothly? What are the things that are needed?
Strong internet connection.
Yes. Okay, internet is one thing. Then what else is required?
A platform like MS Teams or Google Meet.
Okay, that is second. Okay, two. Then
Professor and students.
no, that is okay. That is a physical
Individual
thing. Then
laptop,
what else is required?
individual laptops,
Laptop should be functioning. Yeah, laptop should be functioning. Then what else is required? So I lost your voice. I'm not able to hear. Yes. What else is required?
Energy, time.
power connectivity,
No, I am not talking about those things. I am talking about the components. Okay. So you have not mentioned all those things. See, so device, okay, at the end of student, which includes so mobile or laptop or desktop with all supporting equipment. What is the supporting equipment? That is a speaker, your camera, and then your mic. Okay, all those things are required. Of course, this laptop itself is a unit containing lot of things, but that I am not getting into. Then for professor also you need all these things. That means these units and here even more is required because I have to deliver. So I need, for example, I am using a unit to write, and that unit to write is again a screen, and then there is a pen here, okay, and again this is connected. So all of these things should be functioning in order that this class can be conducted smoothly. So each of them has a reliability, and of course there is a power also. If power is not there, then again things will not work. So you have a system we call what is known as series system and parallel systems. So any system functions provided all parts of it are functioning in various modes. So for example, I will just make one diagram here. So for example, this is the professor's end and this is the student's end here, okay. So in order that this connection is there, for example, I may use say mobile, laptop and desktop. I have say 3 different units arranged here, and so at least one of them should be functioning, and then I have, so with each of them I have some connections, like I mentioned that for the writing I am using a screen, then there is a pen here, and then the internet connection, and then it is transmitted to the end of the student. Again the student is also having the similar things, okay. So if this link is working, then the class can be conducted. If this link is working, then the class can be conducted. If this link is working, then the class can be conducted, okay. Now this link itself has 3 independent links and each of them should be functioning. This is called a series system. Similarly, if I consider this link also has 3 independent components and all of them should be functioning in order that the communication is there from A to B. Similarly, in the third one, these links A to B, A to B, A to B, these 3 different links that I have mentioned, let us call it X1, X2, X3, they are examples of series systems. And these 3 series systems are running in parallel. That means if any of them functions smoothly, then the link from A to B works. This is known as a parallel system. So any engineering system is a combination of various systems which are connected in series as well as in parallel. So the reliability of the whole system will be dependent upon the reliabilities of these individual systems. So let us develop the formula for that, okay. So firstly I consider, is it clear? Is this concept clear?
Yes, sir.
So let us consider a, so this is x1, x2 and so on, xk. Suppose a system has k components connected in a series, okay. Let the system life be x and component lives be x1, x2, xk. So the reliability at time t, that is Rxt, that is probability x greater than t. So if the system is connected in series, then at time t the system will work if each of this is functioning. As I mentioned to you that the component at my end should be function. Hello? Yes? Hello? Is there any question?
No, sir.
So the system will work if the device at my end is functioning, the internet is functioning, and then the device at the student end is functioning. So each of them should be functioning at time t. That means this is nothing but probability of x1 greater than t, x2 greater than t, and so on, xk greater than t. All of them should be functioning. Now, if the component lives are independent, which we can make a safe assumption because device at my end is independent of the device at your end, the internet is independent of the devices, and so on. So if we can assume that the components, if the component lives are assumed to be independent, then Rxt becomes product of the probabilities xi greater than t. That is product of reliabilities of each of the components at time t. So for a series system, the system reliability is product of the individual component reliabilities. Is that clear?
Yes, sir.
And what is an important consequence of it? An important consequence is that since each of these reliability is a number between 0 and 1, so as the number of components increases, the system reliability decreases because you are multiplying each thing with a number less than 1. So more the number of components, the system reliability will become less and less. So that is why many times we talk in a loose term, okay, my system is very good with probability, say 0.9. I mean, so you say that the probability that it is functioning is 0.9. Okay, you can put like that. Now, if you say 0.9 is very good, but if I have two systems, then it will become 0.9 into 0.9, that means it will become 0.81. So suddenly from 90% it has become 80%. Suppose I say I have three systems, then it will become 0.729. So it is coming down to 70%. And you can easily think that what happens if I consider say 10 such things. Okay. So what will be the reliability then? So can anybody tell that?
0.9 to the power 10.
0.9 to the power 10 will become just it is roughly 0.348. So that is nearly 35%. So from a reliability of 0.9, the system reliability becomes very, very low. So that is the consequence, and that therefore the each component reliability should be very, very high. And usually in the engineering systems, so like for example, even your laptop or mobile or any such thing, and now this class is going on. So each of them should have a very, very high reliability in order that the class is conducted smoothly in every class. Like, because I have roughly say close to 40 lectures in a semester, so each of them is conducted smoothly. So all of this should be functioning. That means your network connection, the device at my end, the device at your end, and the power. So all of these things should be having very, very high reliability. I think some of you might have already noted down that sometimes the network with some professor is not working, or sometimes the power failure is there, or sometimes there is a device failure. So you might have noted it here. So if you calculate using the data, so maybe out of 40 lectures you missed 2 lectures due to such things. So then you can look at what is the probability of failure. So 2 by 40 that you are calculating, or 1 by 20, or 5% is the chance that a particular class is not held. Now let us look at parallel. So the concept of parallelism, how it is helpful. So let us consider then the systems connected in parallel. Okay. So this is x1, x2, xk. All right. So this is a so reliability of a parallel system. So suppose a system has k independent connected in parallel. So let us look at the system reliability. That is Rxt, that is probability that x is greater than t. So in a parallel system, the system will function as long as any one of them is working. Okay. So here we can write it as 1 minus probability of x less than or equal to t. Okay. So this means x less than or equal to t means that the system has failed at time t or before time t. So the system will fail in a parallel system if each of them has failed. So for example, it will fail if my laptop is failing, my desktop is failing, and my mobile is also failing. So now if the components are independent, then it becomes the product of the probabilities. So that is nothing but 1 minus reliability of. So this is the formula for the reliability of a system which is having components arranged in parallel. So let us take the previous example where I considered 0.9. Now here you see this product will be decreasing, and then you are saying 1 minus, so it will increase. So here when you add components connected in parallel, the reliability of the system improves. So let us just calculate with 0.9. Suppose we have 10 components with, then what is the answer here? So I will get 1 minus 0.1 . So what do you get? You get 0.999999999. That is 10 times 9 is coming. So system reliability from 0.9, it becomes very, very high if I have 10 components arranged in parallel. So even with if I consider say 2, then it will become 0.99. If I consider 3, then it becomes 0.999 and so on. So this is the effect of parallelism or having additional support in the engineering systems. Is this clear?
Yes, sir.
Yes,
Sir,
sir.
so we can also find this
Yes.
reliability of parallel system by adding the reliability of series systems.
Adding.
Yes, sir.
Where is the addition?
No, sir, I'm telling that we can also find like that also.
No, no. So what is your statement? Tell me again.
Sir, for example, in the parallel system, what every means any one of the series can happen, then system will be working. So for that, for seeing in the series system, we can add up all the series reliability, then we can get the parallel reliability.
So, but then it may get greater than
No, I
one. Like
think
we have to take the
no, I
union,
think
not
you are
the one system.
confused. That is, see, you are telling about this probability of uh, x greater than t. So x greater than t if at least one of them is working, isn't it? So it
Yes,
is
sir.
probability of union of the events xi greater than t, and then you will have to apply the formula for the union. So it will become a bit complex here. That is why I have taken the complementary event, because complementary event gives you the expression very quickly, whereas if you have the other one, then it will be a very long expression. See, if you multiply this product terms, this is like 1 minus y1 into 1 minus y2 into 1 minus yn. So how many terms will be there? So there will be too many terms here coming. So it will be much more complicated formula. Of course, one can do using that, but it is going to be complicated. So in a series system, the reliability decreases with addition of components. In a parallel system, the reliability increases with addition of okay. So that is why in a airplane you will have, in place of I mean in a normal airplane which is like a Airbus or Boeing, Boeing 737 or Airbus 320, you have 4 engine. So even if 1 or 2 engine fail, then the plane continues to fly. Whereas there are many fighter aircrafts and training planes, etc., where you have a single engine, and generally you will see a lot of accidents take place there because it's a single engine thing. So let me just take some example here. So we have A here. We have system reliability for this one as 0.99. Then there are two components connected in parallel. Each of them having reliability 0.95, and then there is a, and again you have say 0.96, say 0.92, and say there is a 0.85. And then you have say another one with 0.95, then there is another one with 0.82. Okay. So this is a certain mechanical system or some engineering system where you have several components which are connected in series, and then some of them have parallelism also. Okay. So for example, this second unit you can see that has two parts. The third unit has three components connected in parallel. This is a single component, this is a single component. What is the system reliability? Okay. Find reliability of this system. So is the problem clear? So the system reliability will be, well, 0.99, that is this first one. Then it will be the second one. Second one you have two of them connected in parallel. So 1 minus 0.95 square. Then you will have third one, 1 minus 0.96, 1 minus 0.92 into, sorry, this will be 1 minus 1 minus 0.96, 1 minus 0.92, 1 minus 0.85, and then you will have multiplied by 0.95 into 0.82. So this will be the system reliability here. That is 0.99 into the second one, it will become 0.9975. Then the third one becomes 0.99952, and then you have 0.95 and 0.82. So this is, after calculation you can easily check. You can see, although the individual component reliabilities are quite high, they are 0.99, 0.95, 0.96, 0.92, etc. The overall system reliability has become much less. It is just 0.7689. That is nearly 77% reliability is there. Okay. This is because so many components are connected in series. So some of them are actually connected in parallel also. So that is increasing the reliability of those parts. So for example, if you look at the second part here, in the second part, individual component reliabilities are 0.95, but this particular part reliability becomes 0.9975. You can see this here. This is 0.9975. Similarly, if you look at the third one, the individual component reliabilities are 0.96, 0.92 and 0.85, but the overall part reliability becomes much higher. It is 0.99952. So you can see that parallelism or having additional components increases the system reliability substantially, which is a very, very common sense thing also. But so in the engineering components, that is what is being done. So even if you look at your laptop, there are so many components there inside that if you open the machinery part of it, and you will find that there are so many parallel connections given there, and because otherwise if any circuit fails or any connection fails, then your laptop will not work. But usually your laptop will work for 3 years or 5 years. I am using is I am using for last 10 years, because there are various things which are in parallel there. So is this problem clear?
Yes, sir.
Yes.
Let me just give one more example. So suppose I have two components, okay. Two components are there and they are connected in, say, okay, let me not make the diagram. Let me write the language here. So we can have them in series and we can have them in parallel. Okay, so I will just take two parts here. Suppose a system has two independent components connected in a series. Okay. The life of first component is variable with alpha is equal to say 0.006 and beta is equal to 0.5. And suppose the second has a life following exponential distribution with 25,000 hours. Okay. So I am just putting some question. So for example, what is the reliability of system at say 2500 hours? Okay. What is the probability that the system will fail before say 2000 hours? What is the system reliability if components are connected in parallel? So is the problem clear?
Yes, sir.
So let us look at the solutions here. So the first one is a Weibull distribution. So if I consider x1 as the uh, first component life, then what is the reliability of this? That is e to the power minus alpha x to the power t to the power beta, t to the power beta. So that is e to the power minus 0.006 t to the power half. And the second component has a exponential distribution, and the life is given as with mean 1 by mean is 25,000. So lambda is 1 by 25,000. Okay. So for x2, so you will have rx2 that is equal to e to the power minus lambda t, that is t divided by 25,000. So individual component reliabilities we are able to find. So what is the system reliability then? So system reliability at time t, that is the product of these two terms, that is e to the power minus 0.006 square root t into e to the power minus t by 25,000. Is that okay?
Yes, sir.
So the first part that is asked is that what is the reliability at the 2500 hours. So Rx 2500, that becomes e to the power minus 0.006 square root t, that will give me 50, and e to the power minus 0.1. So that is equal to e to the power minus 0.4, that is approximately 0.67. So the system reliability at 2500 hours is 2/3. Then the second question that is asked is what is the probability that the system will fail before 2000 hours. So its system will fail before 2000 hours. It is 1 minus the reliability of the system at 2000 hours. So we have already calculated this. So in place of t, you just put 2000 there. So you can easily do the check the calculations. That is 1 minus e to the power minus 0.006 into square root 2000 e to the power minus 2 by 25. So anyway, these calculations can be easily done. That is 0.98. So the probability of the system, okay, there is some mistake here. I think I will not write here the final value, that you can check here. Okay, there is some small error in calculation, so you can check here this value e to the power minus this one. Anyway, you just check this calculation because immediately I cannot use my calculator at this point of time. So just check this thing, what is the value here. Okay. And then the third part is the reliability if the system is connected in if the components are connected in parallel, then you will have one minus e to the power minus 0.006 into 50 and 1 minus e to the power minus 0.1 and 1 minus of this. So you can easily check now that this is approximately 0.98. So it is very interesting. See, if the components were connected in series, the reliability was just 0.67, and if they are connected in parallel, the reliability increases to 0.98, which is very high. Okay. So is this concept clear? The reliability of the series and parallel systems, and of course any general system will be a combination of various such things. Okay. Is it okay?
Yes, sir.
Yes, sir.
Okay. So we now proceed to some other distributions. I will do one or two other minor distributions, and then we take up the important one. So well, I am doing this beta distribution because we have already done gamma distribution, and you had seen that gamma distribution basically, although I gave a derivation using a Poisson process, but actually the distribution becomes more general as a gamma function itself. Okay. So similarly, since you have a beta function, then there is a distribution constructed using that. So a random variable x is said to have a beta distribution with parameters say alpha and beta both are positive if it has PDF So for x lying between 0 to 1, the PDF is x to the power alpha minus 1 into 1 minus x to the power beta minus 1 divided by 1 by beta alpha. So you can easily see, if I consider the integral of this is nothing but beta alpha beta, so it will cancel out and you will get 1. So as I mentioned to you that the form is given because of that. Now there are two parameters, and it can give rise to large number of distributions here by choosing appropriately alpha and beta. Suppose I take alpha is equal to 1 and beta is equal to 1, then it is nothing but the uniform distribution on the interval 0 to 1. Okay. So if alpha is equal to beta is equal to 1, this is uniform 0 1 distribution. That is uniform 0 1 is simply this. But you can see that we can generate many other forms also. Suppose I take here beta is equal to 1, and here I can take alpha is equal to 2, then I will get x. So basically I will calculate this term, that is 1 by beta 2, 1, that is 2. So 2x I will get. Similarly, so if I take various choices, say for example, I take alpha is equal to 2, beta is equal to 1, then the distribution is 2x, 0 less than x less than 1. So what is the form of this distribution? 2x is simply this form. Similarly, if I take say alpha is equal to, so if I increase alpha, suppose I take alpha is equal to 3 and beta is equal to 1, then I will get 3x square. So the form will be what will be the form? It will go like this. So you can see that various kind of shapes can be represented here by choosing appropriately the values of alpha and beta here. See, let me take say alpha is equal to 1 and then beta is equal to 2. Then what will be the distribution? It will become twice 1 minus x. If I take say alpha is equal to 1, beta is equal to 3, then what I will get? It will become 3 1 minus x square. So you have various representations here. For example, if I am having this 2 1 minus x, then it is like this. If I am taking 3 1 minus x square, then it is of this form. Okay. So you can see that various kind of shapes are possible here. Suppose I take x is equal to half, alpha is equal to half, beta is equal to half. Okay. Suppose I take alpha is equal to beta less than 1. Okay. Then the shape will be something like this. Okay. If I take say alpha greater than 1, then the shape will become something like this. Okay. So you can have various shapes. So we can say that beta distribution can be used to model various kinds of data sets. So it is one of the very useful distributions in probability theory. And since the form of the beta function is used, actually you can calculate moments of any order. So for example, what is the general form of kth moment here? It is 0 to 1, 1 by beta alpha beta x to the power alpha plus k minus 1, 1 minus x to the power beta minus 1 dx. So this is nothing but the beta function. So this is Can you see my presentation?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
So here other students are there.
Yes, sir.
Okay. So actually I was talking about the reliability, and now you can see the failure has occurred due to a power failure at my end. So there was a power failure, and it has led to the disruption of the internet connection, and therefore the the communication failed here. So this is a very good example, or you can say immediately. Okay, so this is beta alpha plus k beta divided by beta alpha beta. So you can simplify all of this because you know the formula for the gamma function and so on. So if I am taking the integers or any such thing, then you can easily calculate it, but I don't need to express it here. So if I consider, say, the mean here, that is the expectation of x, that becomes simply alpha divided by alpha plus beta. Similarly, you can calculate, say, second moment, that is alpha into alpha plus 1 divided by alpha plus beta, alpha plus beta plus 1. So mu2 is equal to variance of x, that is equal to alpha beta divided by alpha plus beta square into alpha plus beta plus 1. So this is another distribution which is used for modeling of various kind of data sets. As I shown you that by choosing appropriately alpha and beta, you can have lot of varieties of the curves here. So is it okay?
Yes, sir.
Then another important distribution which is again used quite often is double exponential or Laplace distribution. As the name suggests, actually this distribution arose out of see that in the exponential distribution we have right hand side, but if you have exponential on both the sides, then it becomes a double exponential. So if I consider, say, this, and I consider similar thing on the left also. So let me write here the general form of this one. The general form of course, you had lambda e to the power minus lambda x. So if you put mod of x, then it becomes both side. The general form is written like this: 1 by 2 sigma e to the power minus mod of x minus mu by sigma. Okay, so this is described for the whole of the real line. Actually it is symmetric, so you can easily see that expectation of x will be mu. Okay, in fact median will also be mu, and if you look at the variance, variance of this is 2 sigma square. So I am just leaving it for calculation. You can check all this calculation yourself. You can calculate, for example, quantiles also. Okay, find Q1 and Q3 also. Okay, so I am just leaving it as an exercise for you. Okay, you do these exercises. Let me take another distribution, which is again quite well known. It is Cauchy distribution. Actually, the one of the forms of the Cauchy distribution I gave you earlier, that is 1 by pi 1 by 1 plus x square. Okay, but that form we can generalize little bit, and we can write it as 1 by pi 1 by 1 plus x minus mu square. Okay, where x is from minus infinity to infinity and mu is from minus infinity to infinity. There is another variation of it where sigma is also introduced, but let me not write it here. So if you consider this, the shape is like this. Okay, we have shown that the mean of this distribution does not exist. Okay, mean of this distribution does not exist. So it is symmetric about mu, but the mu is not the mean, but median is mu. Okay, in fact, you can just calculate the CDF here. CDF is integral of this 1 by 1 plus x minus mu square dx from minus infinity to, so let me put it here, t integral from this so that is 1 by pi tan inverse 1 plus tan inverse x minus mu, and at minus infinity this will become minus pi by 2, so it will become plus pi by 2. Okay, so you can see here that at x is equal to mu this will become 0, so you will get half here. Let us also see what are the other quartiles. Suppose I want to find out, so you can say that fx is equal to half when x is equal to mu. So mu is median. Suppose I want to calculate other quartiles also. So for Q1, you will need this to be tan inverse x minus mu plus pi by 2 is equal to 1 by 4. So this gives me tan inverse x minus mu. So this pi by 4 I take to this side and then I put minus pi by 2. So it is minus pi by 4. So you will get x minus mu is equal to minus 1. That means x is equal to mu minus 1. So that is the first quartile. Similarly, if I want to calculate the third quartile for Q3, I will need 1 by pi tan inverse x minus mu plus half is equal to 3 by 4. So a similar calculation can be done. So this gives me tan inverse x minus mu is equal to pi by 4. So x minus mu is equal to 1. This means x is equal to mu plus 1, that is Q3. So we have determined the quartiles of this here. This is mu minus 1, this is mu plus 1 here. Okay. This is Q1, this is Q2, that is the median, and this is Q3. Cauchy distribution is used when the spread is very wide. Here the mean doesn't exist, so that means the tails are heavy here. Okay, the tails are very heavy. So for example, in the case of radioactive decay, because radioactive decay, you know, it is very slow. So for such things, actually Cauchy distribution is more appropriate. A recent example is the COVID curve for India. So there you can see that it is like a Cauchy distribution because it has increased slowly and it is decreasing very slowly here. If you look at the daily cases or the curve for the daily deaths, it is more like a Cauchy distribution. So I just give you an exercise, you can consider fitting of a Cauchy distribution there. Okay. Is it clear?
Yes, sir.
Okay.
Yes. So pi by 2 will come there.
Where?
In
Yeah, this is
Q3.
pi by 2. Yeah, this is okay. Is that okay?
Yes, sir.
So now I move to another important distribution, and in fact, mostly it is considered to be one of the, I mean, mostly are central distributions of the normal of the probability theory. It is known as the normal distribution. Okay. A continuous random variable x is said to have a so I will not call it this one. So here the parameters mu and variance sigma square, if its PDF is given by one by sigma root 2 pi e to the power minus 1 by 2 x minus mu by sigma whole square. Here x is on the whole real line, mu is a real number and sigma is a positive real number. So firstly we will like to look at the shape of this. So easily you can see that it is symmetric about. Okay. Okay, so it is more symmetric around mu. And as sigma increases, the shape will flatten more. Okay. And as sigma decreases, it will concentrate more. So different type of shapes are possible. Okay, depending upon what is the value of sigma here. So the first thing is that let us check the method of calculation for this distribution. So for example, you should have this integral to be 1. So let us establish that. So if you look at this form, it is immediately suggested that we should have a substitution of the type z is equal to x minus mu by sigma. So if you put that, then this integral becomes one by root pi 2 pi e to the power minus t square by 2 dt. So this is an even function. So this becomes 2 by root 2 pi 0 to infinity e to the power minus t square by 2 dt. While doing the gamma function, you would have already done this integral, that this is actually root pi by 2. So this will cancel out, or you will get 1. But if you are not familiar, I mean, you can look at this, the methodology of calculation. You can now put, say, for example, t is, see, this is, I wrote z here, not t. So let me make the corrections here. And now I put here t is equal to z square by 2. So then dt is dz is equal to 1 by root 2 t dt. Okay. So then this I becomes two by root 2 pi 0 to infinity e to the power minus t 1 by root 2 t dt. That is nothing but 1 by root pi t to the power minus half e to the power minus t dt. This is nothing but gamma half, which you know it is equal to root pi. So this is 1. So this is a valid probability density function. Is this integral evaluation clear to you? Is the evaluation of the integral clear to you?
Yes, sir.
Now we can easily go for the calculation of the moments, and from the way we have done this substitution, it is clear that it will be easier to calculate expectation of x minus mu by sigma to the power something, because exactly that substitution we are making. So in place of calculating expectation x square, etc., let us look at expectation of x minus mu by sigma to the power k. So that is x minus mu by sigma to the power k. And we consider the same substitution, so I am not explaining it again. So it is z to the power k 1 by root 2 pi e to the power minus z square by 2 dz. So if k is odd, then this becomes an odd function, so therefore this will always be 0. So if k is odd, then I is always 0, that is mu of k. So if I consider, say, expectation of x minus mu by sigma, because I am taking k equal to 1, then this is 0. This means expectation of x is equal to mu. So mu represents the mean of normal distribution. So this also means that these are central moments. Okay. So now if I consider actually हेलो हम हाँ अभी क्लास अभी है. So what I have calculated here, I have calculated expectation of x minus mu to the power k divided by sigma to the power k. So these expectation of x minus mu to the power k, these then will become central moments, because mu we have shown to be the mean. Okay, so the forms are now, so all odd ordered central moments of a normal distribution vanish. In particular, mu3 is 0. So measure of skewness is also 0. Of course, this is the shape I have shown you, it is perfectly symmetric, so the skewness should be 0. Let us look at now for k is equal to 2m. Okay. Then this mu 2m, it will become 2 times 0 to infinity z to the power 2m 1 by root 2 pi e to the power minus z square by 2. So if we look at that substitution that I did, that z square by 2 is equal to t, then this is 2 by root 2 pi 0 to infinity 2t to the power m e to the power minus t 1 by root 2t dt. So that is nothing but 2 to the power m divided by root pi 0 to infinity t to the power m minus 1 by 2 e to the power minus t dt. So that is 2 to the power m by root pi gamma m plus 1 by 2. And this we know we can expand it, that is m minus half into m minus 3 by 2 and so on up to 3 by 2, 1 by 2, root pi, etc. You will get m minus half, m minus 3 by 2 and so on, 5 by 2, 3 by 2, 1 by 2, root pi. So this cancels out, which you can simplify as 2m minus 1, 2m minus 3 and so on, 5, 3, 1. So mu 2m is this into sigma to the power 2m, because we had put expectation of x minus mu by sigma to the power k. So then the next term becomes sigma to the power 2m, sigma to the power 2m, sigma to the power 2m, and here also you have sigma to the power 2m into sigma to the power 2m. Okay. So if I consider mu 2, that is simply sigma square. That is, sigma square represents variance of normal distribution. Let us look at the fourth central moment here. So mu 4, that becomes 3 sigma to the power 4. So if I look at measure of kurtosis, that is beta 2, that is mu 4 by mu 2 square minus 3. So that is becoming 0. So when I was telling you the kurtosis, we mentioned that there is a leptokurtic curve, then there is a platykurtic, and then there is a normal curve. So the normal curve actually refers to the curve of the normal distribution, and the kurtosis for the normal distribution is actually 0. From the shape of the distribution, you can also see here that mu is the median, it is also the mode. Okay. So median is also mu, mode is also mu. That is, the highest frequency value is also the central value. Is this calculation clear?
Yes, sir.
Okay, so I will stop the class at this point. You please note here that we have a class test on Tuesday, next Tuesday, that is 23rd, between 12 to 1, and also the syllabus for that will be the moments, the moment generating function, the PDF, the CDF, probability mass function, the quartiles, as well as the discrete distributions. Okay, so you have to prepare for that. I will be circulating one assignment by today or tomorrow. Okay. Okay, so shall I stop here?
Yes, sir.
Is there any question? Is there any question?
So,
Okay, so I close the class now.